Okay, here's what happens when I can't go outside and work because it's too hot. I start thinking weird thoughts. So I asked myself, how far above the surface of the earth would I have to travel to feel a significant change in gravity? And so I'm going to use all of Newton's equations here. So his equation, the force of gravity, is big G, the mass of the earth, the little m, which is me, over the radius squared, the radius of the earth, the square. We also know that force can be equated to mass times acceleration. So at the surface of the earth, that would be mass times the little g, which is 9.8 the meters per second squared. So we can equate these to the force equations and get this. mg equals big G, me, the little m over r squared. So we can cancel the little m's. We're just left with G equals the big G me over r squared. This is where this number comes from. This. It was calculated using this to be 9.8 the meters per second squared. So I said, hey, I want to travel a distance h above the earth. So I'm going to call that GH. And so I use the same equation that I have here. The big G me. Now I'm going to add a little bit of h to r plus h, and I'm going to square it. Okay? So from this equation, we see that GME is equal to GR squared. So I take the r squared on the other side. So we can just, this is a constant. So now we can equate this here. So we get GH equals GR squared over r plus h squared. So now what I'm going to do is expand this polynomial. So I get GR squared over r squared plus 2HR plus h squared. I'm going to divide all of this by r squared. So I get G over 1 plus 2h over r. Did I do that right? Yep. Plus h squared over r squared. Now I want to factor this. So I just get GH equals G over 1 plus h over r the squared. Now let's check and make sure this works. So if h equals 0, so I haven't gone anywhere, then this is 0. 1 plus 0 is 0, 1 squared is 1. So GH equal h, that's right. Now what if I went a half the distance up of how long the radius is? So I'm going to go half of 6,380 kilometers. That's the radius of the earth. All right, so I just plug in 1/2 r. The r's, they cancel, and I get G over a 2 1/4. So I invert that and change it into percent. So the gravity at 2,807 kilometers above the earth is only 44% of what we feel right now. So that's interesting. And then I said, well, how far away is the ISS, the Space Station? Well, it's only 420 kilometers above Earth. So if you use this in these equations, it turns out they feel the same gravity we feel. They feel it changes in like the second decimal place or something. There's hardly any change at all. So they feel full gravity. And you say, well, why if they feel full gravity, why are they weightless? Well, they're not weightless. What they're in is free fall. And if they weren't in orbit, they would fall to the earth. The free fall is the same feeling you feel when you're going down a high-speed elevator or when you're going downhill on a roller coaster. So that's what they're feeling is free fall. And they're orbiting at a very high rate to keep from entering the Earth's atmosphere. Anyway, I thought that was fun. I'll see you later.